Hello and welcome to the journey of clean energy from production to storage. My name is Xinran and thank you for joining us today. I'm super excited about the amazing panel of awesome experts to discuss with us today to discuss how they're developing clean technology. And we have live transcript enabled. It's automated, but not always accurate. So please be aware. And you can find it by clicking show subtitles if you want to see it, and you can hide it, hide subtitles to remove it. Right, onto the main event, and it's over to Tom, the co-founder of CO, to introduce today's guests. Over to you, Tom.
Thanks, Shin, and good morning, everyone. Over the next hour, you're going to hear about how scientists could help change the world for the better by changing every stage in the energy life cycle, from generation to storage and distribution. I'm really happy to introduce Leon Devereux, who's a PhD student at the University of Cambridge, who's working on improving solar cell technology. We also have Alice Merryweather, who's also a PhD student at Cambridge, who's studying the processes inside batteries as they operate. And finally, Professor Nick Jenkins, who teaches and researches engineering at Cardiff University and worked in the private sector for some time before that. And we really want this to be interactive, so please don't be shy about asking any questions. The more questions you ask and the more answers you get, the better. If you want to ask anything, please send it to us through the chat function here in the Zoom webinar. Or if you're viewing live on Facebook, then type your question in the comment box and we'll make sure we pass it on to the speakers. I'll just say a quick couple of words about CO, the organisation that's helped put this event together alongside the Rutherford Appleton Laboratory. CO creates events and platforms that give you access to scientists and other experts and hopefully inspire people to pursue careers in science, technology, engineering and mathematics. We're recording today's session and making it available on YouTube, so if you want to watch it again, our account name there is CO.org, that's SCIOORG. It would be great if you could subscribe while you're there. It really helps us a lot. It means we can easily keep you updated with future events. And if you enjoy the panel today, please do share the recording with your friends and anyone who might be interested. We would hugely appreciate that. That is all from me now. Without any further rambling, I'm going to hand over to Leon. Over to you.
Okay, thank you, Tom. I'm just going to get my screen share running. Hopefully everyone can see my opening slide. So, as Tom has said, I'm Leon. I'm at Cambridge doing a PhD in physics, and I'm going to talk about some solar energy generation. So, to start off with, I'm going to talk a little bit about our conventional solar panels that we see on roofs and in fields and things like that. They're quite widespread. I'll talk a little bit about energy levels of electrons in these devices, because that's really what is important when we're thinking about how we harness the energy of the captured light. Then I'm going to talk a bit about these other types of cells called dye-sensitized solar cells. These are what I focus on in my research. And then I'll finish with a bit of summary on efficiencies of these devices and their future. So for regular silicon solar cells, we're all familiar with these sorts of installations, probably. We're seeing them more and more nowadays. But how do they actually work? So they actually have two separate layers, which I've represented in blue and green here. And the blue layer has its outer shell electrons of the silicon at very slightly lower energy than the outer shell electrons of the green region. This is because of different treatments to these two layers. So to actually show this, I've got a little energy diagram here, which has energy on the y-axis here. And we see we've got this kind of plateau region of this orange line, representing the higher energy of these electrons in the green region, and this valley region in the blue area. So this is some outer shell electrons that are lower than this higher region. There's this little cliff in the middle here. Now this is quite a useful picture because generally electrons want to move downhill. Moving downhill is easy, but moving uphill is a lot harder. So this is why we care about these kind of different levels of energy, because then we can see where electrons transfer to and from. We can kind of think of this orange level as a traffic jam, because all of these electrons are in their outer shells of the atoms, but they can't move from one atom to the next. So they're kind of stuck in place because all of the other atoms have their outer shell electrons there as well. But when we absorb light, we can actually kick up an electron out of this blue region, and it's then up onto this other energy level, which I've called a motorway. And this is where it's actually free to move around, so it can actually be conducted, and we can use that to drive it around a circuit and do some useful work. So importantly though, this electron can't move up this cliff, because this cliff is kind of a mimicking shape of the traffic jam cliff that we saw earlier. So this electron is trapped in this blue region effectively. However, this white hole that it leaves behind, this can actually be filled by some of these higher energy electrons up here. So because they like to move downhill, they're going to shuffle down into this gap and replace it. So we actually see that the hole moves in the opposite direction to the electrons moving in, similar to a real traffic jam where you have the spaces between cars kind of close and it shifts back in the other direction. So overall, we've managed to separate our electron and our hole down in the green region. So this electron is then going to go around a circuit, hopefully do some useful thing like power our appliances or maybe charge a battery. And the energy that it releases is this energy gap here between these two levels. This is effectively our voltage across our cell. So that's a quick summary to silicon solar cells, but what I'm now going to talk about are dye-sensitized, and these are much more thin devices that are actually transparent as well. So we can use them to create these window-like structures or lovely colored glass panes that can be incorporated into a whole bunch of different architecture whilst also generating electricity. So these are slightly different in structure. To start off with, we have a base of conducting glass, so it's transparent but also conducts electrons. Then attached to this glass, we have a whole bunch of little nanoparticles, tiny little spheres that are all joined together, that are made of titanium dioxide. And attached to this, because it has a huge surface area, we can fit lots and lots of dye molecules. So these are colored molecules that absorb light. These are what's actually going to be doing the light absorption and kind of harvesting our sun's energy. We can hook this up to a circuit, which I've just given as a resistor here, but we get round to this other electrode on the other side of the cell. And in between these two electrodes, we have what's called a redox solution. And this effectively acts as a charge ferry across the gap between the top electrode and back down to our dyes and nanoparticles. So what will happen is we have light come in, it will hit one of the dyes and excite it so that the electron will get a bunch of energy from the light it absorbs, and then it will get kicked out into the surface that the dye is attached to. So this TiO2 can then conduct the electron round to our circuit, and that will hopefully do some work. And it will then arrive back round to this charge ferry, which I've called, and eventually it will get ferried across over to the dye to regenerate it by replacing the hole that we created in the first place. So to actually look at the energy levels of this, we have a similar picture, but slightly different. We still have the traffic jam and the motorway, this time for the titanium dioxide. But we also have these levels for the dye as well. So before the dye is excited, it's at this position here, where I've labeled it with the relaxed dye. But then when we excite it, it goes up to this higher energy state, which is above the motorway of the titanium dioxide. So this electron can now move onto the motorway because it can easily go downhill. So that transfer is quite easy to do. And then the electron will go around the circuit, release its energy in our appliances, arrive back at the ferry and regenerate the original hole that we created, because the ferry energy level is above that of the relaxed dye. So that is also a downhill transfer. Overall, this is the amount of energy that we've harvested again. So this is our voltage across the cell. It's the difference between the motorway and the ferry this time. So here's a structure of an example dye, which I actually computed myself. Down at the bottom here, we have this anchoring group. So this is a carboxylic acid group for any chemists in the audience. This is what actually binds to the surface of TiO2. And at the top, we have a donor region, which is where the electron starts before we've had any excitation. But it then gets transferred over to an acceptor region when it absorbs the light. So we can kind of think of this blue level as the highest occupied energy level of any electron in the dye. And it's got 2 electrons in it, but we only care about 1 really. When we excite it, it goes up to this lowest unoccupied level, which is in this acceptor region. If there are any undergrad chemists in the audience, you might know a little bit about molecular orbitals. These are effectively just the regions of space where we actually expect the highest occupied energy level to have its electrons. So this is for the highest occupied level, and this is the lowest unoccupied. So you can see at the top, it's mostly up here at the top of the dye, and on the right here, it's mostly down the bottom. And this is important because it's closer, once it's been excited, to the surface of the semiconductor it's attached to. So this means it can quite easily transfer over to the TiO2, this titanium dioxide. But then once it's been transferred, it's much harder to get back to the hole, which is left behind in the donor region. So talking a little bit about efficiencies quickly, the top dye-sensitized solar cells are generally about 14 to 15% if you're very lucky. And the regular silicon solar cells, a bit higher in general. They've been around a lot longer, so we've got better efficiencies out of them. That's not the only reason, but so they tend to be 15 to 20%. The highest commercially available is about 23%, which is pretty good. There are other specialized ones which you can get much higher, but these are kind of the widely available ones we see. Interestingly, dye-sensitized solar cells are also quite good in ambient lighting. So not when the sun is really intense, but rather on a cloudy day, they have something up to 28% efficiency. But the overall power we capture is not as much, like on an absolute scale, if you like. So just to envision a bit of a future for our buildings in cities and things like that, we could have silicon solar panels on our roof, but then tinted glass windows of these dye-sensitized solar cells making up all of the windows. So this would really go a long way to kind of maximizing as much of the area that we have on our buildings to actually harvest the sun's energy, because about 40% of our kind of energy needs come from urban areas. So if we can generate that electricity on demand, on site, then that is great for kind of minimizing all the wastage when it comes to kind of transmitting energy back and forth. So yeah, that is a quick run through of what I do. Questions to follow. Thank you very much for your attention.
Thanks, Leon. Just before I hand this over to Alice, I just had a quick question just that came up at the end there. So as I understand it, the technology, it kind of already exists. Is there any reason for why it's not already being rolled out and sort of put on buildings and stuff? Are we just waiting for it to be a bit more efficient, or is there something else in the way?
Yeah, so well, it is partly there's still development of efficiency going on. There is actually starting to be more movement in developing out in China and like the kind of industrialized Asian areas at the moment. So they are actually starting to get things off the ground a bit more now. But yes, there is also this obstacle still of trying to get efficiencies slightly higher, which is what I'm working on personally. One way in which you can do that is to actually combine two separate dyes on the surface, which absorb in different regions of the solar spectrum. So you get a better coverage overall of kind of all of the light that's coming down onto these devices. Yeah.
Cool. Well, I hope we see some more soon. Thanks for that, Leon. We'll definitely have some questions for you again at the end. Alice, I'm just gonna hand over to you.
Thanks, Tom. Okay, hopefully you can see me, and I'll just get my slides up. All right, hopefully you can see the right slides, me if you can't. But yeah, so I'm Alice, and I'm also a PhD student researcher at Cambridge University, and I'm going to talk a little bit more about the energy storage side of things now. So we've just seen, obviously, a full example of renewable energy production technologies based on harnessing solar power, but generating this renewable energy is really just the first step. So obviously you and I already know that we don't simply attach a solar panel or a wind turbine directly to every device that needs electricity to run. That would certainly make using a mobile phone very impractical. Obviously, that's not what happens. Your phone and other portable devices have got rechargeable batteries inside them, which store that energy so it can be used as it's needed. And if we think about large-scale energy production, obviously we'd like all our electricity to be produced by renewable sources, but unfortunately the sun doesn't always shine, the wind doesn't always blow, so we need to be able to store that energy at the grid level for when it's needed as well. And another very important demand for energy storage, which I'm going to mention, is electric vehicles. So if we can use batteries to store that renewably produced electricity in our cars, we can stop burning petrol and diesel fuel. And in fact, the current government target is to ban the sale of new petrol and diesel cars by 2035. So the race is really on to get battery-powered electric vehicles to the mainstream market. So I mentioned rechargeable batteries a couple of times, so let's have a little look at them in some more detail. And what I'm showing you here is basically the simplified anatomy of a lithium-ion battery. So this is the type of battery you'll already have in your phones and your laptops, and it's similar to the batteries that are going into electric cars as well. Basically, a rechargeable battery like this is a device that can convert electrical energy to stored chemical energy and back again. So this type of battery uses lithium ions to store that charge, which I've represented with the green circles you can see in this picture here. And the battery's got two electrodes. There's an anode on the left and a cathode on the right. And these electrodes are made of specially designed materials that can react with lithium ions and store the ions within the structure of those materials. So the anode is usually made of graphite, which is the same material you might know from pencil lead. There are various different types of cathode material, but the one I'm showing you here is called lithium cobalt oxide. And this is the cathode material you'll most likely find in your phone. So here in this picture, as I've got it there, we're looking at the battery in its state. No lithium inside the graphite anode, but there are some lithium ions already stored inside the cathode material. So this lithium cobalt oxide has got this lovely layered structure, these alternating layers of cobalt ions that I've shown in the green. And this layered structure is really important because it means that the lithium ions can slot in and out of those gaps between the cobalt layers and come in and out of the material. And so that's what happens when you plug in your battery to start charging it. So when you're doing that, connect up your battery to an external circuit and apply a current to the battery. And this means that electrons are flowing around that external circuit. And that leads to a reaction in the cathode material where the lithium ions start to come out of the layers in the lithium cobalt oxide, and they diffuse across the battery through this salt solution in the middle called an electrolyte. And at the same time, lithium ions are reacting with the anode and getting inserted into it. So a bit like the lithium cobalt oxide, the graphite also has this lovely layered structure, which the lithium ions can insert into in the gaps between the carbon layers. So overall in this charging process, the lithium ions have been transferred from being stored in the cathode to being stored in the anode, and so the battery is now charged. And whilst you're using and you're discharging the battery, the opposite process happens. So the lithium ions leave the anode again and they insert back into the cathode. And at the same time, this causes electrons to flow back from the anode to the cathode around that external circuit. And this is what creates the electrical current that you can use to power whatever it is you've plugged your battery into. So what are the challenges associated with these types of battery systems? Well, clearly we want our batteries to be able to store as much charge as possible. And for some applications, we also want the battery to be as small or as lightweight as possible. You might also want to think about how rapidly the energy can be stored or released to charge things up quickly or to release lots of energy quickly. And we also want our batteries to be safe, to be low cost, to use abundant elements and to last a long time and to be recyclable. So there's a lot to optimize to get the best batteries. And battery scientists are exploring all sorts of different electromaterials and different ways of improving the batteries to improve on these qualities. So what I'm going to think about and talk a bit about now is about fast charging batteries. So if a battery scientist wants to be able to take logical steps to improve their battery design to make it charge and discharge faster, they first have to be able to understand what part of the charging and the discharging processes are the slowest and are limiting their charge rate. So we can break down several different fundamental ion transport processes which might be limiting the speeds that the electrodes can operate at. So imagine this yellow hexagon that I'm showing you here is a little particle of material that can store the lithium ions. So for example, that lithium cobalt oxide that I already mentioned. So one battery electrode is going to contain millions of these little particles of active material. In order for a lithium ion, again, a little green fellow there, to be inserted into this particle, firstly, it has to diffuse through that electrolyte salt to get to the particle itself. Then it has to react at the surface of the active particle to cross from that electrolyte into the particle. And this process is called charge transfer. And lastly, the inserted ion to diffuse through that solid particle away from that surface and into the center. And all these processes can occur at different rates, and it can be very difficult to disentangle them and work out which one might be limiting the rate performance of the battery. To observe these processes properly, we also have to be able to make our measurements of our battery whilst it's operating in real time. And for fast charging batteries, this is especially difficult, since the processes that we want to be monitoring are often changing over timescales that are faster than the length of time it takes to make a measurement, with most of the common characterization methods that are out there. So this is kind of where my work comes in. So what I do in my research is I use this specially designed battery cell, which you can see in these images here. It might not look that much like a battery, but it's got all the key components I mentioned stacked up inside it. So we've got the anode at the top here and the cathode at the bottom, which sits just on top of this glass window. So you can see through this photo here, you can see this is the glass window and that black is the cathode, which you can see through it there. And what I do is I put this battery on a specially designed optical microscope, which shines visible light through this window into the battery. And it then collects the light that's reflected or scattered back from the surface of that electrode and records images. So effectively, I'm looking directly into the battery through this glass window to see what's happening inside at the surface of that electrode. Here's a little example image from my microscope of just one active particle of that material, lithium cobalt oxide. So this particle here is about 8 micrometers across, and it's going to be just one of millions in the electrode that I'm looking at. But now while the battery is working, and I'm cycling my battery on my microscope, there are going to be lithium ions going in and out of this material, and there are going to be some really dramatic changes occurring in the material structure, which I can see happening. So I'm going to show you a video of that now. So this is going to be a video where I charge and then I discharge my battery. And to start with, our particle of lithium cobalt oxide is full of lithium ions, and I'm going to be removing them as I charge it. So I'll just play the video and hopefully that works. Okay, cool. So near the start here, if you look at that video on the right, you can see some things starting to move across the particle. And that's a new phase developing in the material, which contains a lower amount of lithium moving across it. And now halfway, I'm going to change, I'm going to start adding lithium back in again. So now I'm discharging my battery. And again, as we get towards the end, that region which I've drawn a box around, you'll start seeing these moving things moving across the particle. And again, that's a new phase time containing lots of lithium ions moving back across the particle to fill it back up with lithium again. So I know that was quite quick to see there, but we can get quite a lot of information about the different processes going on from a video like that. So I'll just finish by going into a little bit more detail about those moving parts that we saw, which was a phase transition. So as you can see here, I've just taken those little parts of the video with the phase transition for the charging on the left and for the discharging on the right. And if you look closely, they're actually behaving quite differently. So for the charging on the left, hopefully you can see that that new phase, which contains less lithium ions, is starting to form all around the edges of the particle and then gradually moving inwards towards a point kind of near the middle. However, for the discharging on the right, the new phase, which is containing more lithium ions than the rest of the particle, this just starts forming at one corner of the particle and spreads out across the particle from just that one corner. And the difference between these two might seem quite subtle, but with the help of some computer simulations, we've been able to show that this difference is caused by a difference in which process is fundamentally limiting the charging and the discharging rate. So here on the charge on the left, this type of behavior shows that it's the diffusion of the lithium ions through the solid material of the particle that's the slowest step. Whereas for the discharge, it's the charge transfer reaction. So remember, that's the insertion of ions at the surface of the particle, which is the rate limiting step. Now, this was quite an exciting result for us because lithium cobalt oxide is an electromaterial that's been around for decades, and yet we were still able to discover something new about it which hadn't yet been shown in years of research. And this is because there aren't really any other widely used methods out there for visualizing this type of ion transport processes on the microscopic scale of individual particles in real time. So it's a really nice demonstration of how new analysis methods can lead to new discoveries, even when a system is already thought to be well understood. So kind of next, moving on, I'm going to be studying some other more recently developed materials, which are kind of more relevant directly for electric vehicles. And I'm going to carry on investigating the fundamental mechanisms which are occurring in these materials at the microscopic scale, and also how these materials degrade and lose their ability to store charge over time. Because the more we understand about these fundamental mechanisms by which these materials are operating, the easier and the faster it will be to improve these battery technologies in the future. So yeah, that's about all I've got time to talk about at the moment. So I'll stop there, but I'll look forward to answering some of your questions a bit later.
Brilliant, thanks, thanks, Alice. It is silly question time from me very, very quickly. Can you give us an idea of like how, because I thought those particles you were showing look really cool, or the kind of how they were filmed. Can you give us an idea of like how small 8 micrometers actually is? That's not going to be visible to the naked eye, right?
No, of course. So a micrometer is it's 1,000th of a millimeter. So if you think of your ruler, your millimeter is 1/10 of a centimeter, so it's 1,000 times smaller even than that.
Okay, that is difficult to compute, but yeah, no, I thought it was really cool. Yeah. Brilliant, thanks very much, Alice. Nick, over to you.
Okay. Where is this gone? Okay, try that. Right. Okay, so I'm Nick Jenkins, and I'm going to give the last of our talks, and I'm really going to focus more on the engineering of how we can use both solar energy, solar panels, and battery energy storage in the electric power system. Now, if I can, there we are. That's my next slide. Okay, so that shows it shows a conventional electric power system, and what we can see, if I can get my pen to work, is sorry, wrong thing. We want the laser pointer. On the left here, we can see the conventional power stations, which still generate most of our electrical, or much of our electrical energy. They make their electricity at a reasonably high voltage at about 25,000 volts. It gets transformed up to 400,000 volts and transmitted into the transmission system, which is there. And that's the thing that moves the electrical power around the country. And you'll have all seen these transmission towers or pylons, and they are taking the bulk electricity around. And then the electricity gets transformed down to a lower voltage through these transformers shown by these double rings to the distributions network, where it is taken where it's used, a lot of it in houses, a lot of it in factories. And that's been around since about 1950 in that form. What we are now doing is we are adding all sorts of renewable energy sources. Here we've got a wind turbine. There we've got a big PV farm. We saw a picture of that in one of the earlier presentations. And increasingly, we are seeing containers full of batteries to provide bulk energy storage. So that's, if you like, connected at really quite a high voltage, somewhere between the high voltage distribution network and the transmission network. So that's one way of installing renewable energy generation onto the network. But the other one is to actually, as we saw again in the earlier presentation, we can have solar panels on the roof. In principle, we can have them within the windows, and we can also have battery energy stores in individual houses. And so that's what's going on. And the whole thrust of this work is to actually reduce the carbon intensity of how we generate and transmit our electrical energy. And in that, the UK has been remarkably successful. There are very, very few coal-fired power stations left. There are gas-fired power stations left, but there is a very big biomass power station in England, and all sorts of wind farms, both onshore and offshore, and increasing amounts of PV farms and PV installations on houses. And the question is, I guess, why we are so interested in energy storage in order to operate this power system. And that's shown in the next slide. And to operate an electrical power system, you must balance the supply and demand of power every second. If you don't, the frequency, which is normally held at very close to 50 hertz, 50 cycles a second, that will deviate from that value, and the whole electricity system will shut down. Now, quite clearly, the solar energy resource varies throughout the year. And an important point is with solar energy is that although it's very important to improve the efficiency of your solar devices that convert sunlight into electrical energy, if you haven't got a good solar resource to start with, then you're really still not going to get very much output. And we can all visualize clearly that the solar resource varies dramatically through the day and the year, particularly in England up at about 50 degrees north, where the climate varies, as I said, dramatically, or the solar resource varies dramatically between January and June. And there are various approaches used to balance the system, and we continue to use gas-fired power generators. We can use pumped hydro, where we're storing water at a height to store energy. We can store dry biomass, or we can demand control. And the important point I'd just like to mention there about the use of gas generators, and still about 40% of our electricity is generated through gas-fired generators, is that fossil fuels are extremely convenient and attractive in terms of the energy density, the density at which they store energy. You can store an awful lot of energy in a high pressure gas pipeline or in a big pile of coal. And that is the big challenge we have as we move towards renewables, which generate electricity directly in response to whether it's the wind power, the wind resource, or the solar resource. It makes the energy and you've got electricity, and you have to use electricity immediately, and you have to maintain this balance between supply and demand. And the only way around that is to store your electricity somehow, either in batteries or in mechanical energy, hydraulic energy, or some other form of energy which can be stored. And the challenge that we currently facing at the moment is that most present battery storage is for 1 or 2 hours. If we go back to this diagram here, there are 50 megawatt batteries being installed, but they will only deliver their full output for about 1 or 2 hours, because that's how they're constructed at the moment. So the challenge we've got is to make the batteries, the big batteries in particular, last much longer while remaining cost effective, which is my last point there. And I think I'll stop at that point. Yeah.
Brilliant, thank you, Nick. And thanks everyone for all the talk so far. I think it's been really interesting stuff. We have got a couple of technical issues, so hopefully you can actually see us all. But if not, if you go onto the gallery view, you will be able to see everyone who's in the room. We have a question in here for Leon. Leon, what are the environmental impacts of manufacturing different types of solar cells? And I guess if I can add something onto that, I mean, are the dye-sensitized cells going to be more or less environmentally harmful to create? How's that going to work?
Yeah, it's a very good and important question. I will be honest, I am less of an expert on the silicon solar cell side of things. But as far as I understand it, there are some quite energy intensive processes in producing these silicon, because you need to treat all of these different surfaces that are involved in kind of forming that layer between the two different regions of the silicon solar cell, and also to get like very clean, to get these clean surfaces, they also use certain quite nasty chemicals, I believe, which are kind of used to kind of rip off any kind of stuff that's sticking to the surface that we don't want there, because it would interfere with all of the kind of actual electron transfer things which I was speaking about. So having said that, the energy costs to produce them has come down massively in even the past decade. So that is definitely a good sign, I think. In terms of the dye-sensitized solar cells, it's still difficult to judge exactly, because we're only just starting to see the real kind of large scale production. And again, I have not done my research per se to know that off the top of my head, but I imagine the most significant kind of costs environmentally to that would be just the actual production of the dye molecules themselves, which will have various chemical industrial processes to actually get the exact correct structure for the actual chemistry to work. There is, of course, the kind of mining the materials of the titanium dioxide and stuff as well, which in general is quite well established already, because TiO2 is actually used in many different products that we already make as well. So things like sun cream is a classic example. So yes, sorry I can't give more detail in terms of this versus that in terms of balance, but yeah, that's what I can think of at the moment. So, but I'm happy to go away and find some links if you are interested, definitely.
Well, definitely, we might be able to circulate some more stuff after the event. I think that would be great. So this question is so it's nominally for everyone, but I'm going to be really unfair and sort of point at Nick first, if that's all right. So we've got a panel here of 2 physicists and one engineer. So I'll ask Nick first, really. But do you find the 2 disciplines do you find that you talk well to each other when that comes up, or is it difficult to speak the same language sometimes?
Okay, on that point, I think we work quite closely with physicists. I did have an interesting experience, some years ago when I worked with a battery chemist. And I was working, in thousands of amps, and he was working in milliamps or microamps. And, the number of orders of magnitudes and the difference in the way we thought about things was an initial challenge. And we had a 3-year project, and it was a very fruitful collaboration, but it did require quite a lot of work to get the communication running.
And Alice and Leon, I mean, to what extent do you deal with the the engineering side of things?
I can jump in there, I guess. I mean, I don't particularly deal that much with the engineering side of things, but I guess a slightly related note, I do kind of cross over between physicists and chemists, and that also in itself is quite interesting, even within scientists, about how these different branches of science think about things in very different ways, and sort of think about how they're explaining things in different ways. In terms of like batteries more generally and this kind of engineering side of things, there are plenty of groups kind of set up to try and translate the findings of fundamental scientists into more engineering type applications and kind of get that transfer of knowledge going. So the Faraday Institution is a big famous one for batteries, which is running at the moment. So yeah, they do exist, but it's sometimes difficult, I think.
Yeah, so my experience has again been that whilst doing a PhD, obviously it's very kind of narrow focus. So there aren't always as many options to do kind of collaborative work with people from other fields. But yeah, I agree. My field is also more linked to chemistry perhaps than like more of the systems engineering field, which is what it sounds like Professor Jenkins's focuses. But having said that, like we do use a lot of engineering principles even in our kind of design of our devices, in the sense that we're trying to kind of either iteratively try to work out what experimentally works better to improve efficiencies, or something which I've been doing more recently, which is actually looking at these huge databases of materials, these dye molecules, and then kind of try to select out using various different rules with computers and calculations that I do on all of these different entries in the database as to which dye molecules will pair up well in these solar cells that I've been looking at. But so that we do definitely take influence from engineering principles. Yeah. Cool.
And we have another question here, which again I think is for everyone, but it's probably best if I ask Nick first. If we look long term at how energy is actually stored and distributed, would it be better to be able for us to produce clean energy locally? For example, using better solar technology and so on, and storing it best through better battery technology. Or would we be better off sort of improving our transmission network? I mean, what do you think would work out best in the long term?
Okay, so thanks very much. Yeah, I think this points to the fundamental problem that we use energy kind of when we want to use it. And so we use in quite varying amounts. So we're going to use a lot of electricity early in the morning when we're all getting up, and it actually peaks also at about 7 o'clock at night when we've all got home and switching on the tellies and things. And then if you think about particularly solar energy, that peaks at solar noon. So we've got this real energy storage problem, unless we can play off multiple loads, which are doing things at different times, and multiple sources of generation. So I'm a great advocate of the interconnected wires that we've got running all over the country for the electricity system. I understand the attractions of operating your own little electricity system, and within limits, I think that's a great idea because it reduces the volume of the flows. But sometimes actually having different sources and multiple different loads is very cost effective.
I'll jump in and I'll jump in and say it's definitely important to acknowledge, like, yes, there are limitations to doing everything kind of on site, so to speak, because like you say, we're very variable in when we decide to actually use the energy. It might not correspond to when it's most available. Yeah, sorry, reiterating your point.
Well, hopefully better batteries can help. And on that point, actually, Alice, we've had a question in here asking whether there are any serious challenges in either the geography or the ethics of where large quantities of lithium and cobalt ores can be mined. Is that an issue?
Yeah, that's a really excellent question, and it's a good point as well, particularly for the cobalt. So for the material I talked about, mostly lithium oxide, the kind of main transition metal that's in that material is cobalt. And cobalt is not really an ideal metal to be using in our batteries because there are only a very limited number of places in the world where they can be mined. I think it's mostly in Africa. And so that's challenging sustainably just in terms of how much material there is to go around. And also there are like some ethical issues associated with the mining practices for cobalt. So as I said, we're developing all sorts of different battery materials, particularly focused on the cathode. And one of the big aims there is to try and reduce the amount of cobalt in these materials to try and minimize some of these issues that we have from sustainability on that side. So like the materials which are going to be going into electric cars are sort of, you can think of it as an adapted form of lithium cobalt oxide, where they substitute out a lot of the cobalt for other elements like nickel and manganese. And these are really the materials which are kind of coming into the mainstream now to kind of take over and reduce that amount of potentially unsustainable cobalt going in there. For the lithium, because that was mentioned in the question as well, it's not quite as much of an issue for the cobalt, but lithium is not the most abundant element. So there is also some more kind of earlier stages battery research going on sodium ion batteries. So it's similar kind of principles to lithium ion batteries, but instead of the lithium ion shuttling backwards and forwards, using sodium instead, which is much more abundant and so potentially more sustainable from that perspective as well. But these are kind of generally in more the early stages of development at the moment.
Fantastic. And I've got a bit of a round robin question for everyone, which we may as well stick to the order that we did the presentations today. I was just wondering what motivated you all to get involved in what you do and what kind of pushed you towards, you know, the careers and specialisms that you've gone for. Leon, what made you get into it?
Yeah, so I'll start off. So I first learned the kind of details of the energy crisis, the looming climate crisis. I say looming, it is already here, and it's we're starting to see the environmental impacts all around the world already. So I first learned about that when I was in kind of late primary school, I suppose. I at that point already got a real passion for science. I was kind of convinced that I wanted to follow some sort of scientific kind of direction, at least for this going on in my school years. And I eventually carried that through to A-level, did physics and chemistry at undergraduate university level. And by the end of that, I found I got quite an interest in the more computational side of doing simulations on the structure of molecules and things like this. So I I had to think, how can I combine these two interests? So combine the need for increasing renewable energy with this interest in the modeling of new molecules and understanding kind of the electron transfer processes in them. And so that led me to these dye-sensitized solar cells, which I now look at because they're a way to harness the sun's light and hopefully contribute in some small way to energy output once we can get them to decent efficiencies. So yeah, that was how I got here.
Brilliant. How about you, Alice?
Yeah, so I guess, so going through school and also through my undergraduate degree, I was always really interested in kind of the crossover parts of physics and chemistry. That was always the area I was kind of focusing on, both from a kind of understanding the fundamental physics and chemistry point of view, and also the challenges associated with how you measure these kinds of processes that I've talked about and that Leon's talked about as well. But actually, the battery side of it, I came to quite late. When I started my PhD, I didn't know much about batteries at all. I was kind of attracted to the idea of my project because of the kind of crossover of the characterization, sort of microscopy elements that I really liked sound of, and also the kind of processes and the kind of solid state chemistry from batteries that I was interested in as well. And that application of batteries I came to quite late, and I sort of only appreciated once I sort of started my PhD the importance of batteries and the whole, how complicated they are, and the whole host of challenges that need to be solved to kind of contribute to this energy storage, to solve these energy storage problems that are so important for our clean energy supply. So yeah.
Great. And Nick, how about you?
Okay, well, I'm afraid I really started with an interest in developing countries. And so I worked abroad for a while. I was actually the engineering manager of BP Solar Pakistan, doing traditional solar panels, but in very remote areas, particularly in Baluchistan. And then then I joined the university, and the interest in renewables just grew and grew and grew, particularly now focused on climate change.
Fantastic. So I think we have time for one quick question. I'm just going to invite someone to jump in rather than asking you all, if that's okay, because we're a little bit squeezed for time. But does anyone have any thoughts on how anyone who's interested in what we've spoken about today, I mean, I guess sort of renewable energy or improving transmission storage or what have you, can get involved? Maybe not necessarily in a careersy way, but how can people help out?
I'm happy to jump in without getting too political. However, there is an increasing amount of politics involved as well. So yes, there's a huge kind of scientific community and innovation community developing around renewable technologies. But if you don't necessarily have that scientific specialism, but are still very keen to see this through, which we all should be, then obviously there's a huge kind of political campaign to transition away from the fossil fuels and see much greater investment in renewables over the next 10 years or so. So there is the ongoing campaign, aimed at primarily fossil fuel companies and lobbyists who have a lot of power over government funding for different energy sectors. So there's definitely a kind of an activism route that we can all take, I think.
Brilliant. Well, everyone, thank you very much for that. That was absolutely fascinating stuff. I'm going to very quickly, if I can ask everyone to stick around for a couple more minutes, I'm going to hand over to Giulio from CO, who's got, among other things, some very exciting news about our next event.
Hello, everyone. I'm Giulio from CO, and I wanted to thank the amazing panelists for such an interesting conversation first. I hope you learn more about clean energy and how it might hopefully change the world. Let's also thank Sophie from the public engagement team at STFC. They were helping us behind the scenes to make this event run smoothly. And of course, thanks to all of the audience for attending this event. At CEO, we want to connect experts to the public. And we had events in the last months hearing from the words of experts in physics, biology, and on various topics spanning from quarks to vaccines. If you missed them, you should definitely go watch them on our YouTube channel, where you can also re-watch this event. Don't miss out on future CEO events. We have plenty of ideas for giving you scientific content straight from the scientist's mouths. Subscribe to our channels on social media. Links are in the chat or in the description on Facebook below. And for the next month, we will not have a virtual event, as we will be live at the IOP Institute of Physics Festival in the Barrowlands in Glasgow. The event is called the Big Bounce. For those who do not know, the Barrowlands are a famous music venue. We won't be playing any music, sadly, but we will be talking about climate change and raising global temperatures with an amazing panel of scientists and activists. If you are in Scotland, you should definitely check it out, and we will post links about it in our social media channels. That's all from me. A big massive thanks to all of you again from myself, Tom and Shinran, and we hope to see you again very soon.